some nice relationships that come out of this. If you just look at this exponential relationship, it turns out that if you take the log of the vapor pressure, you start to get equations that behave very nicely. What you get, the log of the vapor pressure is equal to minus HVAP over R times 1 over temperature plus log of A. And you notice then, this is in this, the form of y equals mx plus b, where y is log vapor pressure, the slope is minus delta HVAP over R, and the x is 1 over t. So the variable that you're plotting against, the x-axis, is 1 over t, and the b is log A. And so what you see is that if you measure the vapor pressure, which is essentially just the amount, the partial pressure of the vapor in the air, so if you can measure the amount of your substance in the air, then you plot log of that by 1 over t, and you can calculate its heat of vaporization, which is a nice effect. This is called the Clausius-Clapeyron equation. And yes, if the pressure is the atmospheric pressure, that would be the boiling point. If you take a pressure, you go over from that pressure till you hit the curve and drop down. That temperature there will tell you at what temperature that it boils at that pressure. Okay. So a nice way to use this, you notice this equation has that annoying log over A, which is an unknown factor we don't have. So let's write our equation at 2 different temperatures. So obviously at a different temperature, you'll have a different vapor pressure. So we have log vapor pressure 1 is equal to minus delta HVAP over R times 1 over T plus log A. And then we also we do the same thing at a second temperature, and of course it'll be that function, it'll be at a different pressure as well. If you're at a different temperature, we'll at a different pressure. So now if we subtract these two, you notice that the log A's disappear once we subtract them. They cancel out. The thing we can't calculate cancels out, and what we get, because when you subtract log of x minus log of y, that's the same thing as log of x over y. Log of P1 vap over P2 vap is equal to delta H vap over R times 1 over T2 minus 1 over T1. So that's the 2-point formula of the Clausius-Clapeyron relationship, which is really nice because it allows you to make a couple measurements and from that estimate the heat of vaporization. Or if you know the heat of vaporization and you know the vapor pressure at one temperature, you can calculate the vapor pressure at another temperature because of this fixed mathematical relationship. Okay, so let's actually work an example here. So let's say we have with the normal boiling point of water. What does normal boiling point mean? Well, normal boiling point just means the boiling point at 1 atmosphere. So it's 100 degrees C, and the heat of vaporization is 40.7 kilojoules per mole. It's an endothermic process. We have to put energy into the system. What is the boiling point of water on the top of Mount Everest, where the partial pressure is only 260 millimeters of mercury? Okay, so we've got the gas constant here in both volume and energy formats, and we've got a nice note that 1 atmosphere is 760 millimeters of mercury, and we've got the Clausius-Clapeyron equation. Let's start just plugging things in. Now, the most important thing to remember when you plug things in, does it matter which one is 1 and which one is 2? It doesn't, as long as you're consistent. So I'm going to start solving it. I'm going to say, let's see, log, and I'm going to choose 260 to be P1, 260 millimeters of mercury, and P2 is 760 millimeters of mercury. Great, and that is equal to delta H vap, which I know, so let's plug that in. It's 40.7 kilojoules per mole, and there's a minus, yeah, there's the minus sign is taken care of in the directions of the T1 and T2. R is, that's the value in joules per mole. I'll write it in kilojoules per mole, so we can kilojoules per mole. So our unit conversions are easy. Okay, now we can cancel those out. And 1 over T1 and T2. So two things that are important here. We've got 1 over T2 minus 1 over T1. So when I picked that 260 millimeters of mercury was P1, that means that's, I've decided which one is temperature 1. Temperature 1 is the boiling point of water on Mount Everest. And so that's actually an unknown. And then since P2 is 760 millimeters of mercury, that means that T2 is the boiling point of water at that place. And so that's where I'm going to put the 100°C. But an important thing to remember in this, as in most physical equations, nature doesn't care where water boils at. Nature uses temperature that's referenced to absolute zero. So we actually have to convert this to Kelvin. You know, the formula only works for Kelvin. So we got 373.15 Kelvin. So that's what we plug in, 373.15 Kelvin. So the algebra is sort of annoying, but it is just straightforward algebra. You know, we can take this side and we multiply by 0.008314 divided by 40.7. And we already canceled out the kilojoules per mole. The log of these two numbers is minus 1.0726, and that is equal to 1 over 373.15 K minus 1x. And so we multiply these together, and then we subtract the 1 over 373 from both sides. We get minus 0.002899. Inverse Kelvin is equal to minus 1 over T1. And so we get the T1 is equal to 345 K, which is the same, which goes into 72°C. So at lower pressures, we have a lower boiling point because as the temperature goes up, it goes up to higher and higher pressures. But here, the temperature at which it reaches 260 millimeters of mercury, and so thus it has, you know, enough pressure to escape from the surface of the water, is into the vapor phase is much lower, only 72°C. So you have a hard time getting a good cup of tea on top of Mount Everest because you simply can't heat the water hot enough. And this is, of course, why pressure cookers work, right? In pressure cookers, you can get up to higher temperatures because you're putting them under maybe an atmosphere and a half or so of pressure. And so you can actually heat it up another 10 or 20 degrees. You can heat it hotter and things cook significantly faster at elevated temperatures. So it's the same idea that you get with your Instant Pot.